How's it going, everybody? This is the first lesson in our new unit all about different counting methods. So the first one is about something called counting principles. And there are going to be a whole bunch of examples and a whole bunch of formulas that we're going to go through, a whole bunch of different situations. But when we talk about counting principles, we're not just talking about like counting on your fingers, like 1, 2, 3. We're not even talking about like skip counting or anything like that. What we're talking about with counting principles is just a fast and easy way that we can figure out the number of ways, the number of outcomes that are possible in a given situation. So we're going to be talking about something called the fundamental counting principle, and then there are going to be some other formulas after that. So the fundamental counting principle is used to determine the possible outcomes for either a single event or a series of events. So it could be one thing happening, or it could be another thing, or like a bunch of things that are happening. When we move on to the next unit, we're going to talk about how does this look like in terms of probability, and we're going to do some probability calculations. There's just another definition here at the top talking about the sample space. So what the sample space is, it is all possible outcomes of whatever the situation is. So example, if we're flipping a coin, we can either get heads or tails. Okay, that is the possible outcome for that event. If we're flipping a coin 5 times or 10 times, that creates a much larger sample space because we have to account for what the results are of each particular flip. So we're going to take a look at our first example here, which says to draw a tree diagram to show all possible boy-girl outcomes if the family has 3 children. Okay, so my 2 different options are boy or girl. So I'm going to simplify that by using B and G. And what a tree diagram is we start with our first outcome. So our first outcome could either be a boy or a girl. So this is my first outcome. Okay, so that's my first child. And then it branches off from there because now when we add the second child, well, it could be a boy or a girl. And if they had a girl first, it could be a boy or a girl. So that is my second outcome. Now there are 3 children here, so each of these are going to branch off one more time. Boy, girl, boy, girl, boy, girl, boy, girl. I didn't mean to put boys first, it's just, boys rule. Just kidding. Okay, so all of the possible outcomes. Well, when we follow each branch of our tree, those are all different outcomes. So my very top branch is boy, boy, boy. So that is my first outcome. My second one is boy, boy, girl. My third one is boy, girl, boy. My fourth one is boy, girl, girl. And then you can do this as well when you are starting with the girl branch. So we have girl, boy, boy. We have girl, boy, girl. Girl, girl, boy. Girl, girl, girl. Okay, so at the end you can see here we have 1, 2, 3, 4, 5, 6, 7, 8. So we do have 8 total possible outcomes here. So we can just go and write down there are 8 outcomes. We have them listed here, and this is what the tree diagram for those outcomes are going to look like. Okay. Example number 2, we're talking about pizza. A restaurant has the following options. So there are 2 choices for meat, either pepperoni or bacon. There are 3 choices for veggies, onions, green pepper, and mushrooms. And we're going to choose 1 meat and 1 vegetable. So how many different pizzas can you make? Well, again, we can make a tree diagram for this where we start with our meat options, pepperoni or bacon. These are our meat options. And then from there, we're going to choose our veggie. So onion, green pepper, mushroom, onion, green pepper, mushroom. This is our veggie option. And there's nothing else that we have to consider beyond this, so we can see that there are 6 possible pizzas. And I'm not going to list them out in this one, but you can go over the different combinations and figure that out for yourself. Now, This tree diagram can get very, very messy because in this case, we only have two different options here. We only had, well, two different categories here with different options. But what happens when you have like a whole bunch of different options? Like it's not feasible. It's very time consuming to make a tree diagram like this. So to make it a little bit easier, there is something called the fundamental counting principle. So what that is the number of different ways that different events can happen is just the number of ways that the first thing can happen times the number of ways that the second way can happen. So if we go back to this first example here, well, there were two options for the first outcome, boy, girl. There were two options for the second child, either a boy, girl, and there are two options for the third one, either a boy or a girl. So using the fundamental counting principle here, there would be 2 times 2 times 2, which is 8 possible outcomes. Okay, and that's using the fundamental counting principle. For the pizza question, there were 2 choices for meat, there were 3 choices for vegetables, so that's where the 6 comes from. There are 6 possible pizzas. Okay, so we're going to be using this fundamental counting principle quite a bit in this lesson to solve different problems. I'm just going to go ahead and highlight this. All right, so example number 3 says, Tracy has 4 shirts and 2 pairs of jeans. How many outfits can she make? Well, the number of shirts and jeans, that's how we would write it in set notation in terms of like the different sets, is just the number of shirts times the number of jeans. So in this case, there are 4 shirts, 2 jeans, times those together, she can make 8 outfits. So a very easy rule to use, but we're going to take a look at some examples in a bit that are going to make it a little bit more complicated. Here in example 4, it says there are certain brand of bikes. They're available in 3 colors, 2 tire types, and 2 different seats. How many different bikes can they make? So the number of bikes using a color and a tire and a seat, again, is just those individual, however many there are of those individual options. So the number of colors times the number of tires times the number of seats, which is 3 times 2 times 2, which is 12 bikes. Right, so I think it's pretty straightforward so far. The fundamental counting principle is just how many things of each thing are there. You multiply them together. On the next page, we have getting a little bit more complicated here. It says a luggage lock opens with a 3-digit code, and each wheel, so each thing on the dial, goes through the digits 0 to 9. How many 3-digit codes are possible? So the digits from 0 to 9, you might think that those are only 9 digits, but if we count 0, that means there are 10 digits that we have to choose from. Okay, so the way that we approach a problem like this, at least for me, is I consider each digit separately, and I think about how many options there are for each digit, and then that is the number that I'm going to write in these spaces here. Okay, so for the first digit, there are 10 options. For the second digit, there are 10 options. For the third digit, there are 10 options. So we're just going to do 10 times 10 times 10, which is 1,000 possible codes. And please, for the love of God, please make sure you are multiplying and not adding them together. These are all multiplication questions. I have seen in the past where people try to add them. That is incorrect. Part B says, what happens if we can only use each digit one time? How many different codes are possible then? Or here's the key word, when repetition is not allowed. That is a very key thing that you're going to see in these problems. So it's a different question than the one we answered in part A. So we still have our 3 digits here. We still have 10 options for the first digit, but now whatever number we put here in the first option cannot be part of the second option. So there are only 9 digits remaining for the second number. And the reason why it's 9, again, is because we used one digit in our first number, in our first slot, I guess, however you want to think about it. Okay, so that's why we're counting down. There are only 9 options left for the second one. And then, now we've used 2 digits, so we only have 8 options left for the third one. So when we multiply these together, we only get 720 possible codes. Okay, so when repetition is not allowed, that is the case where you start to count down your options because you've already used one in the previous slot. Now, one other thing that is important to note is that the fundamental counting principle only works for AND options. Okay, so this is, for example, the first digit, and then options for the second digit, and options for the third digit. It cannot be used for OR situations. So for OR situations, we have to use a different formula. There's actually 2 formulas for it, depending on whether something is mutually exclusive or not. And when we say something is mutually exclusive, that means that they have no outcomes in common. Now, if they have no outcomes in common, we are going to use this formula here. The number of ways that something A can happen or B can happen is equal to just the number of ways A can happen plus the number of ways that B can happen. So it's important to kind of understand the difference between an AND problem and an OR problem. So for example number 6 here. You have a container that has 3 red jelly beans, 2 purple jelly beans, 4 red Swedish fish, and 3 green Swedish fish. So none of these things have any characteristics in common. They are distinct things that are in a container. So this is a case where they are mutually exclusive. They don't have anything in common. So we're going to count the possibilities of picking either a Swedish fish, so any color, or a red jelly bean. So we're going to say the number of ways that we can choose a Swedish fish. I'm going to use S for that. Or, don't forget that symbol, the union symbol we talked about in set theory, a red jelly bean. I'm going to use the letter R for that. So the number of ways we can pick a Swedish fish or a red jelly bean is the number of ways we can pick a Swedish fish plus the number of ways we can pick a red jelly bean. So in total we have 4 red Swedish fish and 3 green Swedish fish. So we have 7 altogether, plus the number of red jelly beans here is 3. So there are 10 possible options for that. Okay, so that's the idea behind mutually exclusive. But if things are not mutually exclusive, which we're going to take a look at in part B, so that means that they do have some kind of characteristic in common. Okay, they have at least one outcome in common. If that is the case, we're going to use this formula here. The only difference between this formula and the previous formula is we need to minus the overlap of whatever those 2 outcomes are. So we're going to take a look at a couple of examples that use this formula to kind of see the difference. So this part B says count the possibilities of picking either a red candy or a jelly bean. So again, I'm going to use the letter R for red candy and J for jelly bean. So the number of ways we can get a red candy or a jelly bean is the number of ways we can get a red candy plus the number of ways we can get a jelly bean minus the number of ways we can get a red candy that is also a jelly bean. So this here is red jelly beans. We're going to minus however many red jelly beans there are from the total. So going back to the previous question, there were 3 red jelly beans. There were 4 Swedish fish. So in total, they were 7 red candies. There were 3 red jelly beans and 2 purple jelly beans. So there are 5 jelly beans altogether. And then we're going to subtract from that the red jelly beans, which was 3, When you add those together, you get 9. So there are 9 possibilities. Now, we use this complicated formula to figure it out, but if we just go back to the question, it does lay out the red candies, and it does lay out the jelly beans. So we know that there are 3 red jelly beans. There were 2 purple jelly beans, so this covers the jelly bean part. There were 4 red Swedish fish, which covers the other half of the red candy part. So if we add those 3 numbers together, we get 9. So the math checks out whether we use the formula or whether we just use common sense based on the information that the question is giving us. Example 7. Consider a deck of cards. So in a deck of cards, there are 52 cards altogether. There are 4 different suits, which are all laid out there. Each suit has 13 cards. There are also colors on the card, so diamonds and hearts are red, spades and clubs are black. There are also 4 aces, 4 of each number, and 4 of each of the face cards. And we're going to assume that there are no jokers in this deck of cards. So in part A, we're going to calculate how many possibilities there are for either a black face card or an ace. So I'm going to call this B, and I'm going to call this A. So the number of ways we can get a black face card or an ace, and I'm just going to write out the formula here using the letters. So the number of black face cards plus the number of aces minus the number of black face cards that are also aces. So the number of black face cards. So there are jacks, queens, and kings are face cards, and each of those has 2 black cards, the spades and the clubs. So in this case, there are 6 face cards that have a black suit. Number of aces, well, we said that there are 4 of each different kind of card, so there are 4 aces in a deck of cards. And then, are there any face cards that are also aces? No, those are 2 completely different things. So these 2 things are mutually exclusive. So we didn't actually need to minus anything in this case because we're minusing 0. There's no possible outcomes there. Okay, when things are mutually exclusive, that means that the number, the overlap, is going to be equal to 0. Okay, so we're just going to do 6 plus 4. There are 10 possible ways of picking either a face card that is black or an ace. But in part B, there is going to be an overlap. So we're looking at either a red card or a 10. So I'm going to use R for red card, and I'm going to use T for 10. So the number of ways that we can pick a red card or a 10 is just the number of red cards plus the number of 10s minus the number of red cards that are also 10s. Okay? So red cards, there are 50-50 red versus black cards in a deck. So there are 52 cards altogether, 26 of them are red. We said for each number there are 4 of each kind, so there are going to be 4 10s. But in this case, these are not mutually exclusive because there are 2 cards that are red and 10. So red 10s. There are 2 of those, the heart and the diamond. So when we add these things together, we get 30 minus 2. There are 28 possibilities. Okay, so make sure that you take some time to understand the difference between and or. Usually it will say it in the question. So these ones have all said or in it, which means that we are using the mutually exclusive or non-mutually exclusive formulas for those. If a question says and, that is your cue to use the fundamental counting principle.